All right. Well, look, good evening, everyone. And look, thank you very much for inviting me along to give a bit of a talk. I haven't given one for about a year, so nice to be asked to do so. Um, Look, just for the record, make you probably all feel a little more comfortable. I used to be VK3 Bravo X-ray from about 1976 to about 1997. So can't take Melbourne out of the boy. So, but now, of course, live in South Australia. So there we go. So look, this is a discussion primarily on magnetic loops or a little bit of low band. It's probably one of my interests. Next to probably 6 meters, but I do love the low bands and how they behave and whatnot. So I can talk on some other things if you want to later on. But predominantly, we'll just do this presentation. It's pretty well rehearsed and pretty well canned. So why don't we start? So I'll share the screen. You'll just have to give me confirmation that you can see my screen there.
Yeah, affirmative, no problem.
Ah, fantastic. Okie dokie. So yes, this is a 160 meter transmitting magnetic loop antenna design, and how the story, the journey of why I wanted to build it, how I built it, and where it finally took us to this day. So let's just see this all works. Okie dokie. So look, I don't like to do death by PowerPoint. I prefer a much more conversational style. So what I would encourage you to do, and look, I guess, Stuart, you might need to keep an eye out for it, but there is a raised hand feature in Zoom, and I don't know if everybody knows how to use that, but you can raise your hand if you want to ask a question. And if that doesn't work, just open up your mic and ask away. But I'd rather deal with the questions then and there. I also say there's no such thing as a silly question. The person sharing this virtual space might have very similar question in their mind, but maybe just not quite prepared to ask the question. So no such thing as a silly question. If I can't answer it, I would take it on notice. That's really all I can say there. Alrighty, well, this is now gets into the crux of it. Have you ever wanted to work the 160 meter band for local and DX contacts? However, you don't have the space to erect a suitable dipole or vertical antenna with its associated tuned ground radial system. Do you suffer from local QRM to the point where most signals or most wanted signals are masked by noise? Do you live on a small allotment or have limited space? Well, a transmitting magnetic loop antenna, or a TMLA, and that's what I'll probably call it from here on in, for the 160 meter band might just be the solution that you're looking for. So what is a TMLA? Well, they're physically small in size with respect to wavelength. They're electrically small with a circumference of around about 10% to 15% of a wavelength. Magnetic loops have a uniform current distribution around the loop. The highest voltage, actually, I'm just going to put my presentation in front of me here. Forgive me, gentlemen, I won't be too, read it a bit better. Yes, the highest voltage appears across the tuning capacitor. So you do have to be very careful. We'll talk about that. When they're working properly, they exhibit very, very narrow bandwidth. To give you some idea, this big one that I've got is only 3 kilohertz wide. So the best I can transmit through it is a single sideband suppressed carrier signal, but it is so critical that you have to put the suppressed carrier, if you're on lower sideband, on the high side of the passband and fill the passband with the audio. So that's how sharp they are, if they're working properly, and that's a dead giveaway. They have a quality factor or Q of somewhere between 500 to 1,000 if they're working properly. My one is about 900. It's enormous. It's a very, very sharp response. This is a really important point. They reject most E-field noise in the near field. And that's great when you've got rooftop solar voltaic arrays and plasma televisions and switch mode power supplies and all these horrible noise generating things near you. They do tend to not respond well to them, as they are predominantly E-field noise producers. They're bidirectional, so they are a dipole per se, with very deep nulls broadside, and that's something we need to talk about. And they also make excellent receiving antennas. I might touch on that after the presentation is finished. So my design criteria, well, I wanted to design a very compact antenna that radiates a reasonable amount of RF power, somewhere between 20 and 45 degrees elevation for DX operation. I might just jump off on a little tangent here because we're going to talk about the vertical radiation pattern and the horizontal radiation pattern. And I just want to make sure up front that we don't misconstrue that as a vertically polarized signal or a horizontally polarized signal. A very simple explanation is the horizontal radiation pattern is just the power that's developed at 360 degrees of azimuth. And the vertical radiation pattern is the other dimension where it's between the horizon and 90 degrees straight up. So I just wanted to make that pretty clear. Sometimes people have got them confused and think that we were talking about a vertically polarized antenna. We'll come to the polarization of a magnetic loop in a little while, but that's when we talk about VRP for vertical radiation pattern or HRP for the horizontal radiation pattern. So anyway, I wanted something in between 20 and 45 because, you know, if you're looking for DX, you've got to get it down that low. And we'll talk about how a loop can achieve that. If it would be good for NVIS or near vertical incidence skywave for short distance comms, so around Australia, that would be a bonus. And a magnetic loop, in actual fact, has its best response straight up. So it's a fantastic NVIS antenna. The second criterion was to come up with a physical design that could be modeled in NEC to see how it would behave, then construct the antenna, and then finally prove the predicted results by empirical field strength measurements in the far field. It's all fine to make antennas, and we all do, and they work really great on the day you use them first up and you have no idea what they're doing. I guess being an ex-broadcaster, you've got to know what your antenna is doing. So for me, the proof has to be in the pudding, and we actually measured it. We'll talk about that. And then finally, to publish the design to allow others to make the antenna with repeatable results, mostly out of items purchased from a hardware store and using basic hand tools. So they were my three criterion. So if you get to know me, if I put something in red, that's a warning, something in green, that's good. So red is something you've really got to take note of here. So the antenna, this particular one, is over 3 meters in diameter. It weighs about 30 kilos. It's not light. The antenna must be mounted on a suitable pole or post and guide for stability. TMLAs exhibit very high voltages and strong magnetic fields. So great care must be taken when choosing a safe position to mount the thing. The antenna needs to be able to be rotatable, as there are pronounced nulls in the HRP. We touched on that. Under 30 degrees in elevation in the VRP. So I'll bring you to a three-dimensional model in a minute, and that'll make a bit more sense, that bullet point. Look, it'll cost you about $800 if you're going to make it. So that's just something you need to keep in mind. Local ground conductivity will affect its performance, depending if it's poor or it's not so good. And there are techniques that you can use to minimize the ground losses. The ground losses are the highest loss in this antenna system. And we'll talk about losses a bit later. And all your connections must be brazed or silver soldered. Any DC resistance is your enemy, and will swamp the queue, and the antenna will behave a bit like a wet noodle. Okie dokie. So I'm not going to get too deeply into this, but just to give you some ideas if you make it properly. And I don't know how well the colors are coming over the Zoom session here, but as you can see, this is a typical, the actual shape of the antenna.
Colors are fine, Sue.
They're good. Okie doke, thank you. With 400 watts RMS, of course, we could never put such power. We can only do 120 watt PY, but if you put 400 watts into it, RMS, you know, up at the top here, you're getting around about 50 odd amps where the capacitor is on this middle crossover loop. You know, you're somewhere around the 57 amp mark. So there's enormous amounts of current flowing here. Hence why resistance of any description is your enemy. So here's another model in NEC, and we'll talk about who did these. I didn't. I'm not an expert in NEC. I do know someone who is. We'll talk about him a little later, but this is just purely the magnetic field of the antenna. So not the E field, it's the H field. And you can see that in actual fact, it's quite directional. Actually, I'll put my laser pointer on here. It's quite directional along the plane of the loop. And you can see these rather drastic nulls broadside to the loop in that, in that plane there. Okay, so here is one now of the actual radiation pattern in 3 dimensions of the antenna. Now, I made a statement before, about its directionality in HRP versus its vertical radiation pattern, and I promised I would explain that. So up at the top here, you can see that the power distribution in nearly all angles of azimuth is pretty uniform. It's lovely and smooth. There's no lobes or lumps or anything like that. And its greatest gain is absolutely straight up and off to the side. So this is a fantastic antenna to communicate anywhere around Australia, New Zealand, Papua New Guinea, that sort of a range on 160, much better on 80. It goes a bit further out than that. However, as you come down in the elevation, you can start to see this null appear here under about 30 degrees. So all I'm trying to say is that for Australia-wide contact, I don't need to steer the loop anywhere. I just about hear everybody, doesn't matter where they're coming from. But if suddenly there's DX coming in at pretty low angles, this starts to play a really big part, and you have to steer the antenna to make sure the plane of the antenna is centered on the DX that you're trying to hear, because this in actual fact is about 25 dB. So if they're weak signals, you won't hear them. They disappear. Now that could be used to your advantage too, by the way. If you've got an interferer on that bearing and you've got the wanted on the other bearing, it's fantastic. But if the interferer and the wanted are on the same bearing, well, you don't win in that respect. This is just a polar plot of the VRP. As you can see, beautiful fellets. It's spherical, it's smooth. There's no lumps or anything horrible. You start to get usable power, in and around here with a maximum straight up, as I said. Just for fun, at the time I had an inverted V, a loaded trapped inverted V dipole, which was my only 160 meter antenna, and I had that model as well, and it had fairly acute angle here, and it was fairly omnidirectional. But you'll see in the next slide here, its useful power doesn't really start till about up here. It really falls off very quickly as you get towards the horizon. So not a great antenna for DX. And that's simply, by the way, I'll just go back. That's simply, by the way, because it was too low. To get any horizontal antenna to radiate at any sort of given low angle, you've got to get it about a half wavelength off the ground. Well, that's 40 meters high. I mean, not in anybody's backyard are you going to do that. So hence, that's another reason for wanting to build a magnetic loop. Okie dokie. So, do's and don'ts. Well, I'm going to call it musts and don'ts. So in making a support structure or a scaffold for it, it's got to be completely non-metallic in its composition. The loop conductor really can only be copper or aluminium, simply because all the current that flows in the primary loop, and that's another distinction I need to make. The primary loop is the big loop on the outside, and the secondary loop is the loop that's coupling energy into it. So both of them really need to be either aluminium or copper. And simply because skin effect takes place and all that current, that 57 amps flows in the first 5 or 6 microns of depth in the copper conductor. So got to have large diameters, but we'll talk about that a little more in a moment. Again, to get as much current flowing, you need the least amount of resistance as possible, so you need the biggest surface area. So again, you try to make the cross-sectional area of the primary loop as large as possible. I'd say 30 millimeters is a minimum, although I'll show you a picture later on of my very antenna design made out of 1/2-inch heliax, and actually works. So not quite as well as something a little bigger, but it actually does work. I settled on waveguide, believe it or not, which was about 38 millimeters across, albeit elliptical, but anyway. So other lossy components in the system, well, you've got to have a capacitor to resonate the thing. And really, you've got to use only capacitors that exhibit low loss. Variable vacuum capacitors are excellent choice. Butterfly capacitors are ideal. What you do have to make sure of course, is the voltage rating of the capacitor is adequate. 400 watts PEP of input power can generate up to 10 kV across the capacitor. So if your capacitor is not rated properly, it'll flash over. You could destroy it, or at worst, get lots of horrible distortion on the air and bad VSWR momentarily. So that's a picture of a Jennings variable vacuum cap, and it's the very cap that's in my antenna. It goes from about 25 picofarads to 500 picofarads. Here's just a picture of a butterfly one. So, you have a fixed status and a rotor in the middle there, and they work really, really well, provided you've got enough spacing for the air dielectric, so it won't arc over. Another really good variety is what they call a piston variety. These work really well. Here's a close-up. Basically, it just has a couple of Teflon inserts inside it, and the plates, one side of the plates are just simply the little metal tubes, aluminium tubes running up the inside, and the other plates are the outside tubes there. They work really well, very low loss. You might have one of these in your junk box maybe. This is, I think, a Hammond one. Is a 200 picofarad unit. Nice big gaps for air spacing. This is not a good capacitor to use for a magnetic loop. And the reason is it has a commutator at the end here. And this commutator will put resistance into the system, and the resistance of that commutator will absolutely swamp the Q, and the antenna will behave like a wet noodle. Do not use a capacitor that has any commutation at all. They don't work properly for higher power applications. Look, another little thing that I see from time to time, and I just like to point it out for potential instructors, or constructors, should I say. So here's one made out of a bicycle rim. That's pretty cool. You've got the capacitor up at the top here to resonate the thing, and you've got your secondary loop down the bottom. And this is the correct way to make one. Many times I see them made like this. Now they work. What they do is they put the actual secondary coupling loop up at the top, and they put all the tuning components down at the bottom. And as I mentioned before, the biggest source of loss in a transmitting magnetic loop antenna is our ground losses. So why on earth would you put your high impedance point right next to Earth? It's beyond me. Why would you do that? It's incorrect. You shouldn't do that. You should have them the other way around. You should put all the nice high impedance stuff up at the top and feed him down at the bottom. That's just a little tip. They work. There's no question they work. It's just these work better. And silver solder or braze all your connections. As I say, DC resistance is your enemy. So, how do you work this out when you've constructed such an antenna? Well, this is the 4-wire Kelvin method. You'll never get a multimeter that will read down to milliohms. They're just not common. So the easiest way to do it is just have a DC source, an ammeter, some resistance wire, and a voltmeter across the what you're trying to measure. And it's just simply then Ohm's law. So in my case, 0.07 of a volt across the capacitor, or where the capacitor would be, about 7 amps flowing. Do the math, you get about 10 milliohms. That's where you want to be with one of these antennas, and that's for a really big one. The smaller ones, that goes down to 0.005, 0.002 if you construct them properly. The other thing you've got to do for your secondary coupling loop is you also use coax that's got a solid outer. So you know, RG213 or RG8, or you'll see people make loops with these things. They're not very good. The skin effect performance is nowhere near as good as a solid outer conductor. So that's a Faraday shielded one. I'll do a close up in the middle, but if you can get yourself some LDF 450 and the associated connector, these are absolutely ideal. And you simply just got to make sure everything's soldered or silver soldered or brazed properly. And then you've got to make sure they're weatherproof. So that's just got vulcanized, you know, self-amalgamating tape on it, and then PVC to keep the UV out of it. The other thing that you have to do, a transmitting magnetic loop antenna is actually a balanced antenna. It is truly a dipole antenna. Yet here we are feeding the thing with unbalanced transmission line. If you don't decouple that transmission line at the feed point, you're simply, irrespective of the return loss or the VSWR of that antenna at resonance, you're going to get currents that flow back along the coaxial cable. And those currents, if you're transmitting, flow along the cable, but they're also there when you're receiving. So suddenly your transmission line system starts to become part of the antenna, and that's something you do not want. So the only way to sort that out in this particular design is if you've got to use a common mode choke at the feed point. Now, this is very important of what I'm about to say. Ferrite or magnetic ferrite materials come in all sorts of different permeabilities, and that's all dependent on frequency. So this particular one here is a very big one. That's a 4-inch toroid, and it's type 77. So I think it's got a mu-I of about 2500. And I've wound it, I think it's called Grignella or split phase style, where you'll have, how many have I got here? I've got 1, 2, 3, 4, 5, 6, 7. So I've got 8 windings one way, and then we go anti-phase and do 8 windings the other way. Now, I've measured this, its inductance, and at 1.8 megs, it exhibits about 10k ohms. So it's an absolute open circuit to RF. But the reason that we do them anti-phase is if you don't do that, you start to get some auto transformer action going on, and voltages at the antenna end on the outer of the coax start to rise. So doing it this way, you just cancels out those voltages, and it stays nice and cold and decouples the antenna beautifully. So just be wary about what magnetic materials that you use. I will tell you a little story a little later on in the presentation. Then you've got all these other things that connect to the antenna. You've got rotator wires, and you've got DC cables to adjust the little DC motor and so on and so forth. And they're all right in the near field of the antenna. And of course they get voltages induced into them. So you've got to decouple them as well. You don't want them to be part of the antenna system. And just some more pictures of what I had to do. Again, that was a further one down the transmission line. That absolutely cleaned it up for me in this particular instance. Okie doke, you've got to try and make the antenna rotatable. There are significant nulls present in the HRP, as we talked about before, and just to refresh your memory, that's here. These nulls are quite deep and will affect very low signals. Good waterproofing techniques. So I just used an old jerry can, you know. Oh no, it was a new one at the time. Just did a little bit of surgery on it, and that's a complete rain cover. The bottom's open, so there's no condensation issues or whatever. And that's been up for 5 years or 4.5 years now, and I haven't had any trouble whatsoever with that. Trying to mount the antenna at least 2 loop diameters above the ground. Where possible. Now that's very difficult on 160 meters because theoretically that should be 6 or 7 meters above the ground, but in my case I could only get it up to about 1.6 meters at that point, and it does affect the performance of the antenna, I might add. So do all these metal fences around it. I mean, at the end of the day, I live in suburbia, and then you've got to guide the antenna for stability. Alrighty. So that's a little bit about musts and don'ts. So the design and construction phase. A few statements. This is pretty much out of Krause's antenna handbook, but a small magnetic loop antenna is defined of having approximately 1/10 of a wavelength in circumference. And this equates to approximately 16 meters on the 160 meter band. And using the circumference, the diameter of the loop would be approximately 5.2 meters in diameter. That's a pretty big structure. If you ever think about it, you've got to build a scaffold for it. So I decided that size was too large to be manageable and to create a structure to hold it. So in searching the internet for designs, it led me to begin considering a two-turn magnetic loop. Sorry, I'll just turn that off. Although it is my XYL, we communicate via text in this house. It's quite funny, so I better check something here in case the house is burning down. No. Okay.
The sad part is when it's from the next room.
Yeah, well, she's upstairs. Anyway, no, nothing particular untoward, and I'm going to put that on silent now so I didn't hear. Okie doke. Yes, so yes, I started to consider a two-turn design, approximately half the diameter. So we'll call it a solenoid because that's what it is. It's a solenoid. So in the end, I ended up making the antenna two loops approximately 3 meters in diameter. And I found that 10% was something that you could expand on, because remember, the actual efficiency of the antenna is a function of the enclosed loop area. So the more enclosed loop area you can have, the more efficient the antenna will be. So I found, in actual fact, that about 15% of a wavelength, about 23 meters. Now, I always say 23 meters because that gives you a little bit of room to cut a bit off when you're making this thing, rather than try and add a bit on because you made it too short. In actual fact, it comes in at around about 21 meters or thereabouts. So anyway, it's a sweet spot. And I only found that out by empirical measure. So 15% for a two-turn holds true. And it holds true even when you scale it, which is really good. So I used Heliax. Heliax, for those who don't know, is not only coax, but it's also a waveguide, sold as waveguide, which was used for the main loops. It's like coaxial cable, but it has a solid copper sheath, but there's nothing inside it but air, and that makes it a little bit lighter, which is really good. But it still gives you the cross-sectional area to make a magnetic loop antenna work. And I managed to get some 7 gig waveguide off a tower that was being decommissioned, and I knew of that tower, and rather than go to the metal recycler, I think I came up with a case of Cooper's Pale Ale, and it ended up in my trailer, which was pretty good. So there's a photo of the said waveguide with all the fittings on it. And this was in our testing phase, but it's just a good photo of what it looks like all coiled up. So a TMLA needs to be brought into resonance to work, as I discussed before. This is done by connecting a capacitor in parallel with the primary loop inductor. And as I mentioned, I used the Jennings 25 to 500 puff variable vacuum capacitor, and that one's rated at 15 kV. So more than enough to handle 400 watts PEP of input power. Now, theoretically, and I stress theoretically, this could handle a kilowatt RMS all day, but you know, I'll never know that, will I? It's just a theoretical power input. If you wanted to make a single loop, of course, it would require a much larger capacitor, because by doubling the turns, you quadruple the inductance, so therefore you only need 1/4 of the capacity. So the other benefit in that, it does make for a cheaper tuning capacitor. Picture again of said capacitor. Here's just some photos of how I mounted it, just on a bit of nylon cutting board. That's a little DC motor. It's got a little gearbox on the front of it. That's a 12-volt unit rated at 10 revolutions per minute, but you need much slower than that to get the granularity that you seek, and I'll show you that. This part of the capacitor here came with the capacitor. That's a ceramic isolator, so it allows mechanical energy through it to turn it, but because the ceramic material is an insulator, it doesn't stop any RF getting back onto the motor. Just another view from another angle. bit of a close-up of it. So you can see the arrangement. You've got these metal, I don't even know what you call them, but you know, they're mounted at 90 degrees to one another with, of course, the ceramic as the in-between. So I touched before about how to slow it down. This is just a cheap and cheerful little Chinese reversible DC power supply, but it uses pulse width modulation to actually regulate the voltage and thus slow the motor down. But it still provides oodles of current, and therefore the motor doesn't lose torque at really low speeds. So this is a little video I'm about to show you here of the said system. So that's the little power supply, that's the little 10 RPM motor, the whole capacitor. This is just a simple multimeter that's reading in picofarads. So that's 295 picofarads at that point, and you'll see the capacitor about half a mesh there. So what I'm going to do when I run the video, I'll run it fast, I'll slow it down one way, I'll click the reversing switch, run it slow, and then fast the other way. You'll get the idea. Here it comes. If I can turn off my laser pointer. Yep, here we go. So it's pulling the plates apart. And of course the capacitance is dropping. It's sped up. And I'm slowing it right down. And you start to get about 1 puff per second. That's about your target rate to tune a magnetic loop. That's what you need. Or a stepper motor, which we'll talk about a little bit later on. So, and that's just spinning it back the other way. So very simple system, no software required, no drivers required. It's all manual. It's still what I use on the big loop to this very day. I'll touch upon why in a minute, but that's a good little video of how it all kind of works. There's just a drawing of, you know, basic sizes. You know, it's, as I said, it's about 3 meters. Whoops, I'll put my laser pointer back on. It's about 3 meters in diameter. It's about 600 millimeters apart. You can see one loop gets onto the other loop by simply going over the top. Right at the very top there is the 0 voltage point. And then of course, either side here, of course, is the maximum voltage across the antenna. So give you some idea. And the top loop just clears the other loops by about 150 millimeters. So I'm giving you a little bit of giveaway here. One thing about this antenna, much to my surprise, and I didn't know it would do this, but whilst it works on 160 meters, and we'll talk about its efficiency and so on in a moment, it is spectacular on 80 meters. So I get 1 octave out of it. Similarly, when I scaled them up, if I make one for, I made one for the 60 meter band, on 5 megahertz, and guess what? It goes to 10 megahertz beautifully. So this design actually gives you 1 octave. You get 2 bands if you have the right size cap.
May I pose a question?
Of course you may.
In regard to the design there. In regard to where the crossover, where the loop occurs, you have it raised at the middle. Is there any electrical reason for that, or was it just convenience?
Purely mechanical.
All right, so it could be running on the same plane.
If you wanted it to, absolutely.
Thank you.
No worries. So there's a picture of the scaffold. So I just choose 50 millimeter PVC piping and fittings. So that made it really easy. It was just like Meccano, to be honest. These were all bought from Perf Irrigation, if you're ever looking for them. It's all on my website, by the way, which I'll point you to in a minute. But yeah, just send them money and they send you all the bits back. It was great. This is the antenna disassembled. One of the things that we did find, though, and I'll just go back here. So I had to put a piece of timber inside here that it just wasn't stiff enough when you got the weight of the waveguide around it. So ultimately what I had to do was put a piece of timber in the bottom section and about halfway into the top section, and that completely solved the problem of mechanical stability. And it keeps the timber weatherproof and everything like that too. So that's just a picture of it on its side. There you go. You can see the timber inside the middle crossover bit. So that was in the very early phases. That was just fitment. So that was just making sure I had enough waveguide, note the extra overhangs and so on here. But that just made sure that the piece that I had cut off was the correct length and fitted nicely. I then had to manufacture my own little I don't know what you'd call them, feed through holders, if you like. So all I did to do that was just buy the PVC end caps and bore a 38mm hole in the top of them and glue them onto a bit of pipe, and that holds the waveguide quite nicely, as you can see. And then it was a matter of just fitting the motor and the vacuum cap, and again, it's very important when you're making connections to the vacuum capacitor. You've got to use copper or aluminium with a very, very large cross-sectional area for a skin effect. So that's I think that's about 50 or 60mm copper strap that connects to either side of the capacitor. I'll give you some close-ups of that in a moment. So that's what I call a little bit of copper origami. You know, how do you get things out? So I just folded it over so I could bring it out at 90 degrees, sorry, 180 degrees to the other side. You can see it all sort of sat there quite nicely. Now, all just bolted just for getting it all to be mechanically right. And this is a bit bush and home brew, to be honest. I'm going to show you an example of a much better one that someone else copied a little later on. So, and again, just to get the fitment right, and then ultimately my very poor attempt at brazing, but it worked. And then waterproofing everything so that tarnish wouldn't develop, because tarnish is a resistance. It sits on the skin of the conductor and can add to resistance. And I keep harping on that resistance is your enemy. So tarnish is not a good thing. There's just a photo of the secondary loop in construction. We've seen that before. Just again soldered, waterproofed. Okie doke. So this was, I'd finished the antenna, and this was my little temporary area for putting it up. Now, a couple of stories here. First of all, you need to understand that my wife is very, I guess, tolerant of my amateur radio activities. I'm lucky enough to have a 17-meter tower in my yard and all sorts of other bits and pieces, and she's pretty good, but she did not like this antenna one little bit. As a matter of fact, that's where I wanted to put it, and she said if it's going to go there, she was going to leave, and it better get packed up and get put in the shed. So, boy, oh boy, that was a bit hard to take. I've got to tell you. But the other story around this, and you've got to take very careful note here. So have a look at the secondary loop. So it is about 600mm in diameter. Now I'm going to explain to you how you calculate the secondary loop size. It's very simply about 1/5 of the diameter of your magnetic loop. Well, traps for young players here. So I made a magnetic loop that's 3 meters in diameter or thereabouts. So, you know, roughly 1/5 of that's about, you know, 600 mils or thereabouts. So I put that all in and got it all there and put my VNA on it, and I was rewarded with a return loss of 6 dB, which at resonance, by the way, which equates to a VSWR of 3:1. Not very good at all. As a matter of fact, it was terrible. I really couldn't continue at that point. So I remember ringing Lee Turner, who I talked about before, VK5KLT, or his new call sign VK5LT. He is a professor at Adelaide University. He's a specialist in magnetism. He holds an enormous amount of patents, worldwide patents for RFID technology. He is a doyen and has done some fantastic work. If you look up any of his papers, as a matter of fact, if you go to my website, the first thing I direct you to is to read his paper on magnetic loops. So I rang him up and crying on his shoulder, and I'd spent a month, by the way, at this point, getting this all together, and rewarded with a SWR of 3:1. And so he was very calm and considerate and listened and started asking me a few questions and said, well, you know, what diameter is your secondary loop? I said, oh, about 600 mils. He said, and how did you come up with that? And I explained it, and he said, Steve, whilst you have made a solenoid, it is still got to be considered a single turn, and that is about 5.2 meters in diameter. This has to be bigger. So that one got ripped out. And here now is a photo of the final installation. This is about 920 millimeters in diameter. Now, I played around with it because I'd already then discovered that I was going to get another octave out of it and it would work on the 80 meter band. So when I made it 900 millimeters in diameter, I was rewarded with a return loss of about 17.5 dB, which in actual fact is about 1.3 to 1 on the 160 meter band. Very happy at this point. That's excellent. My transmitter will be happy. But then after a little bit of empirical playing around with size, look at that, about the same return loss on the 80 meter band. So now I have an antenna that exhibits about 1.3 to 1 on both bands. How happy was I? Except I had nowhere to put it. So anyway, Lee came over and he spied my vegetable patch, which is sort of way down the bottom of the garden, but it's a bit lower than where I had it. I'll just go back to here. Up here, the vegetable patch is to the right here. As you can see, the land slopes away pretty fast. And he said, well, why don't you put it there? And I said, oh, but the fence and the hill and the dirt. And he said, Steve, from what you've told me, that if your wife doesn't like it here, you're not going to be able to put it up. And he said, what use is an antenna that's packed up away and put in your shed? And I said, well, not much. So I quickly disassembled the whole antenna, put it down into the vegetable patch and called my wife out to the balcony. And I said, well, what do you think of that mounting position? And she said, and it's hidden by trees. And she said, well, I can't see it. And I said, well, it's down there. And she goes, well, that's okay. You can have it there. I'll be honest with you and tell you that the concrete that was holding in the supporting post was drying 4 hours later. So that's where it actually ended up. Okie doke. So now we've got a working antenna. You know, how on earth do you know that it's working properly except but to measurement? So I pulled it all apart and packed it all up and took it out to a local park where I set it up as a test size. And you note the 900 odd millimeter secondary loop now. So I guess the question was, how on earth do we measure the vertical radiation pattern? How do we measure that angle? So I came up with an idea of just using an equilateral triangle as part of the test jig and flying a field intensity meter at 45 degrees to it. So we could, and I was only more interested in the 0 to 45 degrees on how much power would be radiated there. So that was the idea. And this is where Paul Lawson, who is the person, VK5 Sierra Lima, he's the person who did all the NEC for me, all the NEC calculations. He is an expert in MF and HF, especially in measurement. So he came along with a field intensity meter, which is here, and we found a tree with a suitable limb that was high enough to make an equilateral triangle. So that's the field intensity meter. It's got a little antenna, a little loop antenna in the lid is how it works, but you can see we've gone to great trouble to make sure that there's nothing metallic around it. And in fact, a couple of ropes either side to be able to twist it back and forward. And you'll see a tape measure hanging down underneath it. So that will then read off in distance above the ground. And of course, we can work out the angle at that point. Here's another picture looking back. So there's the field intensity meter being flown. You can see the magnetic loop over on the other leg of the equilateral triangle. And anyway, I guess the argument put to me was, well, how on earth are we going to be able to read the meter when it's up at full height? And I suggested we just get a pair of binoculars. And they went, oh yeah, that's a pretty good idea. So a pair of binoculars it was. But anyway, there is the field intensity meter flown up at 45 degrees to the antenna. Anyway, it was a complete failure, total disaster. Didn't get one measurement out of it. And it took a minute to work out why. And I'll tell you that story in a second, but this is a magnetic loop. Magnetic loops in the near field are only an H field. They are not an EH field. They're not an electromagnetic wave. They're a magnetic component predominantly only. this meter only responds to an EM wave, not a magnetic wave. And it was in the near field. And we found that the near field of this antenna actually extended out to about 0.5 kilometer. So we had to take this thing 0.5 kilometer away to even start getting readings and be able to work out the horizontal radiation pattern. So to this day, I cannot tell you categorically what the actual vertical radiation pattern is. I can tell you by NEC calculus that what it should do, and I can tell you empirically that it certainly works DX, but I have no way of knowing what the VRP is. Now, that's not going to be remaining a mystery for too much longer. I have a colleague in the broadcasting game who started his own business measuring antennas using drones, and Paul 5SL has built him up a probe, an EM probe that sits on the bottom of his drone, so he can measure MF antennas and the HF antennas and the like. So he promised me the next job he ever gets in Adelaide, COVID permitting, he's actually going to come over and fly my antenna, and he'll plot that pattern for me, and then I'll ultimately know. But until that day, I can't tell you exactly what it's doing. Can tell you what it's doing in the horizontal though, because we could measure it. So one of the things Paul Lawson wanted me to do, he was just wanting to see what effect the ground would have on the antenna. So you can see these 8 radials flying up from the underneath the rotator, and the antenna's up just above here. And he wanted to see what the behavior was like with and without the radials. And in my case, it was only poor to medium ground conductivity and really didn't affect the performance of the antenna whatsoever. Instinctually, you would think having a really, really good ground would be beneficial, and in actual fact, it's not. It's the other way around. Really good ground will soak up a lot of the magnetism. These things work actually best in the desert, where there's probably just silica. Okie doke, so there's the antenna in its glory under test. Now, I've got a couple of little videos here for you just to show you the bandwidth of the antenna on 160 meters. So let me give you the setup here. So the meter here is reading VSWR. At the moment, the pointer is on 3 to 1. There's 2 to 1, 1.5 to 1, 1 to 1, and the like. And I'm just going to put a carrier into it. And then what I'm going to do is I'm going to change frequency and go up in frequency, and you will see the actual VSWR dip to where the antenna comes into resonance, and then go back up again. So we're going to look at the 3 to 1 VSWR bandwidth. So take a note of the frequency. It's about 1.858, say. Here we go. Watch. I'll just get rid of my laser pointer. Okay, here we go. So you can see it's about 4 kilohertz wide. I'll do it again. Very narrow. And that's the sort of performance that you want to expect if you've built one of these things properly. As you go higher in frequency, you get wider bandwidth. The lower in frequency you go with respect to the diameter, of course, the less efficient and the less bandwidth that you have. This will just give you an idea of the tuning speed of the antenna just with the little DC motor. So you'll see on the waterfall display here, I'm going to give you a better demonstration live of this after my my PowerPoint presentation here, but you'll just see the speed of it as it rolls across the screen. So you can just see the resonance point moving up in frequency. So I've left the frequency. You can see a big peak. I'll go back to that in a moment. But you can see here the receiver now being quite deaf when it's not resonant. This is a really good thing. I'll explain why in a moment, but I'll just run the video again, and you can just watch it. As it comes into resonance, you'll see the noise peak. So you're just looking at the S meter now. And then it dies off. So the antenna in its own right is a natural filter. So you've already got a filter for your antenna. It's not a wideband antenna, it's a very narrowband antenna. It's got a couple of pluses. So noise power is greatly reduced because the receiver's only getting the noise power pretty much in the resonant part of the antenna, which is only 3 kilohertz odd wide. The other thing where it absolutely shines is with lightning or that sort of static impulse noise. Again, you're not getting the whole wideband noise hitting your antenna and then hitting your receiver. You're only getting 3 kilohertz of that great big pulse. So therefore, it's much easier to listen to other stations in lightning. I mean, unless they're running a loop, they can't hear you, but you can hear them. Okie doke. So there's a picture of it in its final installation. All the components, obviously the waveguide around the outside, the secondary loop made out of LDF 450. There's the little common mode choke, the rotator underneath it, the secondary loop made out of LDF 450, the guying that I talked about, the weather cover and so on and so forth. And it looks quite nice. I had to make a little cross piece at the top. I had to try and guy it 4 ways, but to do that, I had to get 2 of the guys actually out of the actual center of the antenna, otherwise it would foul. So I had to do that. I'll show you a magnificent alternative to that a little bit later in the presentation. Okay, so here's a video of the actual antenna being rotated. And you can see it rotates beautifully. Very stable. And there you go. Just a bit of a close-up of the weather cover, although you've seen that before. You've seen that shot before, again, looking up at the little motor and the variable vacuum capacitor. I just use great big cable ties to keep everything centered. The waveguide's got Heliax ripples in it, so it bites on quite nicely. This is just a still shot. This is back when I still had my inverted V. Now this was taken during the day, and you can see the resonant portion of the V is down this end of the band. It wasn't particularly good. Well, obviously we're not allowed to even transmit up there, but you can see it was more resonant down here. Now this was taken during the day with all sorts of, you know, solar arrays going and switch mode power supplies and so forth. And you can see the noise is pretty high. I'll give you a much better demonstration of this after my PowerPoint presentation, if time permits. But you can see it's nearly 10 over 9 as far as noise is concerned. Now and by the way, this was just switching between this antenna and then the magnetic loop. And you can see there's nearly 30 dB of noise reduction there. It's phenomenal. It just doesn't respond to the noise at all, except where it's resonant. So, you know, from what, S5.5 to +10, same instant, same day, same noise. So they really are great receiving antennas too. Alrighty, well, it's all fine to sit here and talk to you about making it and so on and so forth. We amateurs, we're interested in results, aren't we? I mean, we want to work DX. We want to try and get those bits of wallpaper like I have behind me. Okie dokie. So since February 2016, that's when I put it in. On 160, that is. I've worked 42 DXCC confirmed, which is no mean feat for a tiny, tiny little antenna on a suburban block. And, you know, whilst Tonga's not very far away, or Norfolk Island's or New Zealand's just across the way or whatever, but, you know, USA, Germany, Italy, Finland, for goodness sake. My first contact was with Lithuania, and all sorts of other places in between. I've been heard in South America. SWL sent me a card. I've never made a contact yet into Argentina or in the southern part of South America. Nor have I worked Africa. I nearly got one last season, and the season was around about January, February. But unfortunately, he was DX and the wall of Europe, and he couldn't hear me. So anyway, it works. That was my very first contact on it for DX, LY7M in Lithuania. I couldn't believe it. and he confirmed it, which was very satisfying. This was just this is a particularly good night. I don't know how much experience you gentlemen have, or ladies and gentlemen, if you've got any ladies in the audience, but have had on 160 meters, but it's a very unpredictable band. You can't really predict how it's gonna work from one day to the next. This was just a good night, and only works in darkness, of course, for DX. It's not a daytime band at all. D-layer absorption just kills it off. But you can see I was working up here into the Philippines, and then into Japan, and into Asiatic Russia and North America, and that was on CW. That was a good night, all off this tiny little antenna. Probably one of my most proudest ones. Was when they had the Heard Island expedition down there in the Arctic Ocean. I just had a feeling that it was going to be a very good morning. So you can see just about at my grey line, and we weren't too far away. I think this one was, what date was this? Does it say here? Yeah, it was in March. So we're just approaching the equinox, which is also a good hunting time for grey line for us. So it's just approaching the dawn, and I was listening for them, and they were actively spotting on the cluster. And I was listening, and they're in the noise. I could hear them, and they just came up and up and up as the dawn approached. And when I worked them, they were about 10 dB over 9, and I worked them first shot and got a confirmed card off them. So that was probably my rarest DX on 160. It was really fulfilling. When you put it on a map, it looks pretty impressive. That probably needs to be updated a bit. There's certainly more contacts than that these days. That's 160. On 80, it goes berserk. I mean, on 80, I've got a DXCC on 80. That's amazing. So here's, now I don't know, again, I could be being called a heretic here. Some people like FT8, some people think it's a terrible mode. My own personal opinion, it's just another mode. I quite enjoy it, simply because there are many stations that I have DXCC status on that I could never have worked, because that's all they were working was FT8. This was a really good night on 80 meters with the antenna, and just to give you some idea, I was truly illuminating the dark side of the Northern Hemisphere on my little tiny magnetic loop. I don't know what else to say. It just it works particularly well, especially for the poor signal to noise ratio modes. But people were hearing me really, really well. And then similarly, again, just after equinox, again, right at our grey line. I mean, look at that. I've lit up Europe, for goodness sake, on 80. So, you know, if you're looking for a compact antenna on 80 meters that's going to work infinitely better than your horizontal dipole that's maybe 10 to 15 meters off the ground, this is an antenna worth considering. And again, that can only show you the results. So that was a good night. And, you know, I was getting some good signal to noise, you know, -13, -13. That's a bit hard to read here, -8. For some reason, the Canary Islands there's a pipeline to VK5. You just don't know why. It always good signals to the Canary Islands. So anyway, works really well. Look, I haven't got the audio hooked up. This was just a Hungarian station. I might be able to see if I can just turn it up. I don't know if will work. We'll try it. Let's see if you can just hear it through my microphone here. Oh, next to a speaker. That was receiving on the magnetic loop. I didn't work him that particular day, but he was coming in over 9. Lovely signal, but they've got pretty serious stations that they use and lots of power. Okie dokie, so now is a bit of a time to whet your appetite and just give you some ideas of what other people have done and how you can build these things. So I have a very dear friend of mine who was also part of this mentoring group with magnetic loops. His name is Trevor. He lives up in the Adelaide Hills. You'll never hear him on air, unfortunately. He doesn't like to talk, but he likes to build things. So he made a double turn loop just using Heliax coax. It's not my design. what I liked about it and why I put the slide here is simply his method for rotating it. So it's a gate hinge, if you like. So this part here will fold out to here, so you can move it through 180 degrees because it's on a hinge. Really cool, really clever. I just thought, wow, never even considered that idea. Another good friend of mine who used to work for me many years ago, his name's Steve, got to be a good fella, VK7 Oscar. You probably hear him in RD contests. He's into slow scan. If you're ever watching slow scan, you'd know him. So he, before he moved in Hobart, lived on a postage stamp of land. So that between here and here is probably 5 meters, 4 meters if you're lucky. So he decided that he was going to build my full-size one and stick it up in his backyard. So he used LDF 450 because he wanted to keep it really lightweight. And it works. He's worked DX on that antenna out of this postage stamp of a backyard on 160 meters and 80 meters. Quite extraordinary. VK1KF in Canberra. He decided he'd build one, which was very flattering. This is his first iteration. He made a bit of a mistake, and I'll tell you a couple of stories in a minute, but you've got to read the instructions. You can't deviate. This antenna has to be made as the designer tells you to make it, or it won't work properly. His spacing between the loops is too narrow here, and you get some horrible phase cancellations, and it works like a wet noodle. And we worked out very quickly what was going on, and as soon as he spaced them out to 600 millimeter spacing, it worked as it should. So just traps for young players. His is really impressive. He got it up really high, and it works particularly well. That's that one. Here comes a story. So this is my good friend Kamal, 4S7AB in Sri Lanka. So he contacted me and said, look, you know, I read your article. I really want to make this antenna. Looks fantastic. I said, look, no problem. And I might add, there's been about 35 of these made, by the way, worldwide, which is very pleasing. And all constructors, after they've fixed little faults that they might have introduced, all actually say to me that it behaves as I described, which is really pleasing. The next thing that we did, which was probably the most pleasing thing to me, is we did an FT8 contact, SFA loop to SFA loop on 160 meters. So that very antenna and my very antenna made a QSO on FT8. Signal to noise was probably around about the neg 20, but it was a valid QSO nonetheless. So that was particularly pleasing. This is the king of installations. This guy, Bob, KO2F, he took it to a whole new level. So first of all, it looks really nice for a start. It's lovely and circular and so forth. His idea of a frame is the best I've ever seen. It's just absolutely brilliant. So he set it in concrete. There's just no chance of the wind ever blowing it over. It moves beautifully through 360 degrees of azimuth. No metallic structure whatsoever to upset the magnetic field. The only thing that I would do differently, having seen his idea, and I am going to do it one day, is I would make these support posts longer, and I would make this 2 sections either side actually slidable, a bit like a reverse sash window, if you like, and have a pulley arrangement where I could actually lift it up higher. So I could lift it down to work on it and lift it up high for operation and just shove some bolts through it or something like that. But he sent me that photo. He lives in North Carolina, and I think he's got the XCC on it, which is just fantastic. And again, he saw the article. Look, there's just a photo of a small 40-meter version that I just knocked up for fun for field day. So that was activating that was, I think, the Murray Alta Conservation Park there, Paul PAS. I think I even talked to you on it, I think, on that particular day. Works really well. So then I got a bit loopy and decided, well, I wonder if they'll scale up to VHF. So that little fellow there is one that I made for the 6-meter band, and it is absolutely tiny. So its components are the 2 turns in scale, variable vacuum cap to resonate it. There's the common mode choke at 6 meters, which in actual fact is RG58 in many terms, which is a lot of inductance. and it's only 200 millimeters in diameter, and it throws off a 6-meter wave like you have no idea. When I transmit on that, people cannot believe the signal strength that I put around Adelaide on that tiny little thing. As a matter of fact, I did this presentation down at the Southeast Radio Group in Mount Gambier, and they do the fox hunting, which I'm sure you VK3s would know all about and take part in. They're very good hosts for that. And one of the foxes saw this thing, and he just had to have all the dimensions and how to make it, because he felt that would be a very, very misleading antenna because of its radiation pattern. You'd be driving around and you'd get into its null and suddenly you'd lose it and you'd think it's on another bearing. So he's made one of them. So look out, all you 6-meter DX fox hunters. It's going to be a hard one to find. So then that was all good. I thought, well, okay, it's terrific. It's all manually tuned. So in conjunction with a really good programmer, now I'm not a good programmer, but I do know how to specify what I want in code. I got a young fellow that used to work for me to come up with a system to automatically tune it. So I then built a scale model. So this is for the 60-meter band for when we ever get it. So this will go from 5 megs to 10 megs. Obviously can use it on 40 and 30 meters. This one uses a stepper motor to drive a much smaller variable vacuum capacitor. I'm not sure if I've got a close-up of that. No, I don't. But that's a little 5 to 100 picofarad Jennings, again, rated at 15 kV, so it can take some power. So this all runs under Linux, and I might add at the outset, I've actually abandoned this project. I just want to show you what we achieved. The issue for me was one of temperature variability affecting the tuning, and the backlash that's inherent in all variable vacuum capacitors. Not so much in butterflies, but there is backlash, and the calibration goes out really, really quickly. But anyway, we wrote a bit of code. It worked using hamlib to be able to talk to all different brands of transceivers and so on and so forth. So I'll give you the quick setup here. I'll show you how well it worked when it worked, but unfortunately, it just on the lower bands where tuning is even more critical, it just wasn't satisfactory. It wasn't repeatable. But anyway, what we have here, this is just a Windows PC with a web browser that's looking at my little Raspberry Pi. Here is a little IC706. It's just got a forward and reverse speeding power, or SWR and forward power meter on it. I've got the microphone in my hand. I'm not turning the VFO dial. I'm just using the up and down buttons on the microphone. What you'll see is it's communicating via CIV protocol, the ICOM protocol, into the Raspberry Pi. Here in the software, you'll see the frequency displayed. Here you will see the number of steps forward or backward, and what step it's actually kind of going up to. So I'll just run it. You'll see, again, I'll try and give you some sound with this. What you will see is the antenna start in resonance with a minimum VSWR. I'll change the frequency. It'll instantly go out of resonance. And then you'll see the system wind the capacitor up to bring it back into resonance. And there's no feedback on this system. It relies on you calibrating it and telling it where all the steps have to be for any particular given frequency. So anyway, we'll give it a go, and you can just see kind of where I got to, and I'll try and give you a little bit of sound. Here we go. And there you go. So that was quite a bit of fun. It wasted about 6 months, but I learned a lot of things about it, which was pretty cool. I ended up going up. There's a gentleman, I forget his call sign, but Loftur Johannesson. He's a Icelandic Canadian. He came from Iceland. He's written a beautiful controller which I built, and it takes care of the backlash issue. You can null that out of it, and it works particularly well. So anyway, it was just a bit of fun, all part of the learning curve. And then there was the competition. A friend of mine over here, Grant, VK5GR, some of you may know him, worked in Keen DXer. He encouraged me to enter it simply because the antenna design, or my end design, actually fitted within their criteria of a 30 by 50 foot area and stand no taller than 30 feet in their money. So I decided I'd enter it. Grant helped me with the presentation. He's very, very good at graphic design. Any rate, I entered that in, I think it was about April of 2018. In October, I got an email, and that was the email I got. I couldn't believe it, which was just absolutely fantastic. And then they subsequently published the antenna in the 2018 QST and the design competition. So that was great. And whilst I won $1,000, which was fantastic, more importantly, it got published and lots of people saw it and piqued their interest, and they built them. And there's more people on 160 meters and 80 meters now. So there we go. So that there pretty much concludes the presentation per se.